Yeah, welcome to the live session on uh, question and answers for the course Scanning Electron Ion Probe Microscopy in Material Characterization. I would be happy if you have any questions or if anyone is online. Please go ahead. Welcome to the live session on question and answers for the course Scanning Electron Ion Probe Microscopy in Material Characterization. I would be happy if you have any questions.
Mute your YouTube audio.
If there is no one or uh, if there may be questions, before that let me begin with some of the questions came in the forum so that you might have your queries clear. Or if in the meantime, if you have any questions, please go ahead in asking. There is no one or if there So first is the resolution, which is one of the very important aspects of the microscopy, any kind of microscope. Here we talk about the scanning electron microscope. The definition of resolution is always same. For any microscope, particularly, it is defined as the closest spacing between the 2 points that can be seen through a microscope as separate entities. So how two objects or 2 points can be placed as close as possible, still we will be able to see them as 2 different entities. So that smallest distance or the smallest gap between the 2 points that we could measure while distinguishing these 2 points as separate entities is called the resolution. Now, resolution primarily depends on the wavelength of the light or electrons or ions. And in this course, we have talked about the electron and ion particularly. We have not covered on the optical microscope where light is used. Now, electron wavelength can be as small as in the nanometer scale. In case of ion, the wavelength will be even much smaller. Therefore, ion microscope, particularly helium ion microscope, can give us better resolution. So resolution is directly depends on the wavelength. Smaller the wavelength, better will be the resolution. The gap between the 2 points can be small. And it is inversely proportional to the angle of aperture, which is alpha. Angle of aperture more means R value, or resolution value can be small. But when angle of aperture become more, the beam diameter will be small and also resolution will be higher. At the same time, the depth of field come into picture. And there are few questions on comparison of resolution and depth of field. For a higher depth of field, we need to have a smaller angle of aperture, that is alpha. So now, I have already told what is resolution, that is nothing but the closest spacing of 2 points that can be seen through the microscope as separate entities. Similarly, for the definition of the depth of field, it is the range of position of the objects that can be viewed by the microscope without losing its sharpness. That is the depth of field. Now, there are some confusion of some students regarding what actually the depth of field. So I take a simple example here to make you understand more about depth of field. For example, there are 100 rows in a classroom and teacher sitting in the front. So if I put a camera and try to take a photographs, it may not be possible to have a same focus in the photographs for all 100 rods. If I take a photographs, I would probably able to focus first few rods, let's say first 5 rods, or somewhere in the middle of the 5 rods, or towards the end of the 5 rods. If I collect, let's say, a photographs where only 5 rods in the classroom are well focused, and rest of the rods are not focused, then that 5 rods, distance of the 5 rods is my depth of field. So if I reduce my angle of aperture alpha, then I can have more depth of field, like more number of rods can be under focus if I reduce my angle of aperture. By reducing the angle of aperture, automatically my beam size increases. My beam size increases, and that it covers larger area certainly, and I could collect photographs where more number of rods are within focus. But at the same time, I cannot have a highest resolution, because for highest resolution, my beam diameter should be very small. As I told you, as soon as I reduce my angle of aperture, my beam diameter will increase. Beam diameter more means my resolution become poor. So that's in order to have a better or higher depth of field or more number of rods in the classroom to be focused, I should reduce the angle of aperture alpha, and that can be done by the microscope. But if I want to take a high resolution image, then I should have a very small probe dia. The diameter of my electron beam should be small, so that information will come from a smaller area of the sample. So in order to do that, so my angle of aperture has to be large. Angle of aperture has to be large. So as per our resolution formula, R is equal to 0.61 lambda divided by alpha, we will have a better resolution. So, and that would happen when you already you use a larger angle of aperture, automatically working distance also decreases. Working distance is the distance between your lens to the sample surface. So in order to have a image with a larger depth of field, we should use a smaller angle of aperture, alpha. And that would allow us to see larger area because your beam diameter is more, and also more number of features on the samples are well focused. And at that place, if as I am looking for a larger area of the sample, I am less concerned about the resolution. Resolution will be important when I magnify a smaller region of the sample and see them clearly. So when I look at the smaller region, then only my resolution will be very important, at very high magnification. So in order to focus a smaller area, my beam, electron beam size should be as small as possible. So to do that, I suppose to have a large angle of aperture, and that would give me higher resolution, because my probe diameter or electron beam diameter or ion beam diameter will be very small. So another question was there, that whether resolution depends on the incident electron wavelength or secondary electron wavelength. Certainly, as I told, resolution depends on the incident electron wavelength. Therefore, our helium ion microscope gives better resolution because the ions have a smaller wavelength as compared to the electrons. Similarly, electron microscope has a better resolution than light microscope because electrons could have a smaller wavelength. But the other points was whether it depends on the secondary electron wavelength. Okay, so let it not be confused with secondary electron wavelength and incident electron wavelength. Okay, so incident means you mean primary electron beam. Yes, resolution depends on the primary electron beam. And the secondary electrons, which is generated from the sample surface, which is used for microscopy purpose, we do not care about the wavelength of those electrons. If you remember, the definition of the secondary electrons are the electrons which have an energy less than 50 electron volt. Which have an energy less than 50 electron volt, we say those as a secondary electrons. We do not separate out the secondary electrons which has 10 electron volt or which has 15 electron volt, because then again their wavelength will be changed. We do not separate out. So those all the electrons which have energy less than 50 electron volt are called secondary electrons. And the secondary electrons are the signal of our electron microscope, and also the ion microscope. So now more number of secondary electrons generated from the surface, more signal is generated. Therefore, that would help us to have a better signal to noise ratio. We would expect that more number of secondary electrons generated from a smaller area so that we can make our electron beam as small as possible. Because as soon as we reduce the beam diameter or electron beam probe size, then interaction volume decreases. So number of secondary electrons released from the sample will be less and less, unless and until we have enough number of secondary electrons emerging from the sample, which is nothing but signal. We cannot have a good brightness contrast difference. So because our at least the brightness contrast difference should be at the level of around 5 times. So our peak or the number of electrons which is generated should be at least 5 times that of the background. So that is called signal to noise ratio. If the signal is at least 5 times that of noise, then we can distinctly see the brightness contrast difference, and that would gives us a 3-dimensional image. So remember, it is secondary electron wavelength is not important in case of scanning electron microscope or scanning ion microscope. The wavelength of the primary electron beam or primary ion is important for the resolution. But even though the wavelength of the secondary electrons are not important, the number of secondary electrons generated from the sample is important for getting a good resolution image, high resolution image. Because if we get smaller number of electrons, then signal is less, and that much of signal will not be enough for us to create a image or a brightness contrast difference. So therefore, the wavelength of the primary electrons is related to the resolution. On the other hand, the number of secondary electrons is related to the resolution, but not the wavelength of the secondary electrons. So this is the difference between the resolution and depth of field. Another question was which electron gun is good for scanning electron microscope. We have discussed about 4 different types of electron guns. One is thermionic gun, which is based on the tungsten filament. Then we have another thermionic gun, which is based on the lanthanum hexaboride filament. And then third one is field emission gun, which is again tungsten tip, but very sharp tip. Electric field is used to take out an electron through a tunneling phenomenon. And then fourth one is our short key emission gun, which is again that tungsten one, but coated with a zirconia. So now 4 different electron gun. Which gun is best for microscopy purpose or best resolution? Field emission gun, FESEM, or that is what we say, field emission gun is the best suited for high resolution image. But to see the features of very small size, we should use field emission gun. So like if you have like say carbon nanotube or anything of nanometer of size, diameter, etc., then you should choose field emission gun. Then what is when should you choose short key emission gun? Short key emission is again, it has both field emission phenomena and thermionic phenomena, where the tip is heated to a little high temperature and also field is applied. So in case of short key emission gun, we have a zirconia coated tungsten filament, and the zirconia coated tungsten filament is good for high stability. Because zirconia, as you know, is an oxide material. So for that oxide material, the little bit of pore vacuum in the chamber or could be acceptable, unlike the field emission gun. In case of field emission gun, our tip size is very small. Tip size is approximately, if I remember correctly, the tip size is around 2 to 5 nanometer, less than 5 nanometer in case of field emission gun. Or that is also we say cold field emission gun because that is operated at the room temperature. The tip size is less than 5 nanometer means the electrons which are generated from a smaller area, therefore you can confine them to be much smaller beam diameter, and then beam diameter can be very small. Therefore, you can get a high resolution image. In comparison, Schottky emission gun, which is nothing but zirconia coated tungsten, where the tip diameter is a little larger, that is around 15 to 30 nanometer. 15 to 30 nanometer, as the beam diameter is the source diameter. Source means the electron gun diameter itself is larger. So therefore, the beam diameter will also be directly related. We cannot get as small electron beam dia like that of cold field emission gun. However, the stability is higher in case of Schottky field emission gun. If you are doing, you are going to do use biological sample or type of sample which is like gel or a liquid type of sample, which you have to froze it and do it, then you should preferably choose Schottky field emission gun, because this type of biological sample always produce some kind of water vapors under electron beam, and then a small water vapors will not damage or will not damage the tip or electron gun to a great extent as that will do with cold field emission gun. First of all, in case of cold field emission gun, the prop size is very small, so therefore little contamination inside the chamber or pore vacuum is not at all acceptable. Moreover, the lifetime is almost same for both cold field emission gun and also Schottky emission gun, as compared to those are much higher as compared to our tungsten thermionic gun and LAV6 gun. Another point is that energy spread. Energy spread is nothing but the energy of the electron beam coming from the cold field emission gun and Schottky field emission gun. The energy spread is less in case of field emission gun as compared to the thermionic gun. Therefore, they are suitable because they will give a less chromatic aberration, because chromatic aberration depends on the delay, directly proportional to the energy spread, and therefore less aberration. So the conclusion is that for high resolution image, you should use cold field emission gun. Otherwise, if you have biological sample which you also need to study at high resolution, then one should use Schottky field emission gun for its for long time stability and long time use. There was another question about the detection of zinc and copper in case of alloy. It's difficult using the EDX, energy dispersive X-ray analysis. It is difficult, but it is not impossible. We can certainly detect zinc and copper in a sample, in the same sample. I have given an example that, for example, one type of X-rays have a higher energy X-rays, which characteristic X-rays which coming from the, let's say coming from the zinc, have a higher energy. That example was given to a size of the energy value was 8 point something. That yes, the zinc K alpha energy is 8.64 kilo electron volt, which can excite the copper X-rays. That means zinc K alpha X-rays, which is generated from the zinc copper alloy, can be used to excite or can be used or utilized to make another transition in case of copper, which needs less than 8.6 per kilo electron volt energy. And this makes the elemental analysis difficult. Yes, it is true, but you do not have only K alpha, you have also K beta, M alpha, and other characteristic X-rays present in those samples, and they would not be utilized for making other transition unless until they are available. So even though one type of characteristic X-rays is utilized for making another transition, but you have you can use other characteristic X-rays for measuring the elemental composition quantitatively. So it is not. It is difficult, but not. It is not impossible. And we regularly measure zinc, copper alloy, or all the silicon, aluminum in the same sample can be measured. That is, and it gives approximately correct results. Another question is that there was a question that low energy gives high resolution due to surface interaction volume. Low energy gives high resolution. As per that, this statement is not correct because low energy gives produce higher wavelength. High energy acceleration voltage produce smaller wavelength. Smaller the wavelength, better will be resolution. So in that regard, if you want high resolution, theoretically, you should use you should use a higher energy acceleration voltage or higher acceleration voltage to get higher energy of the electron beam so that you can get smaller wavelength. But in some cases, you cannot use high energy electron beam because it may damage the sample. And another issue is that higher energy electron beam will penetrate more deeper into the sample. And therefore, its interaction volume will also be large. So if we talk about the interaction volume, then the person who has asked this question, he is correct. When we want the signals to come from a smaller area, smaller interaction volume. If the information come from a larger area, then our resolutions will certainly be poor. So there is an optimum. You cannot for an optimum, and also it depends on the sample to sample. Like if you have a oxide kind of sample or metallic kind of sample, you have no problem to use high acceleration voltage or high energy beam. For example, you have a gold sample, then if you take a higher acceleration voltage or high energy electron beam, then you get best resolution as compared to the samples such as, let's say, a carbon or say polymer kind of sample or some materials which has lower atomic number elements. In the lower atomic number elements or materials where electron beam can penetrate much deeper if you use high energy electron beam, and then the information will come from a larger area. So practically, you should choose less than 5 kilo electron volt for high resolution image for any kind of sample, practically. Moreover, if you have a polymer biological sample, you should certainly choose less than 1 kilo electron volt for collecting the best resolution surface image. If you have a like ceramic sample, or yes, another type of sample is like a insulating sample. Insulating sample, certainly first of all it will give charging. It will have a charging effect, and the charging effect will be much stronger when you use high energy electron beam. So that would be another problem. So for insulating sample, you should use the low energy electron beam, which has a less electron beam current. Another question on EDAX was why wavelength dispersive X-ray is not extensively used even though having high resolution. Yes, though I have not covered much of the wavelength WDX, wavelength dispersive X-ray spectroscopy, but the principle of EDX and WDX is slightly different. In the energy dispersive external analysis, we measure the energy of the X-rays that are generated from the sample. We just directly measure the energy of the X-rays. And how X-rays are generated? Our sample is incident with an electron beam, and when electron beam incident on the sample, those can create a vacancy at the inner shell of an atom. So now, in order to fill that vacancy of the inner shell of an atom, an electron from outer level jumps back to the inner shell, and thus producing the X-rays. As all atoms in the periodic table have different electron configuration and their energy level difference, energy difference between different levels are different. Therefore, they all produce different X-rays energy. And just directly measuring those X-ray energy, we tell which element is present, which atom is present in our sample. In case of WDS, also that happens. X-ray is generated when electron beam strikes on the sample. X-ray is generated, but all X-rays that are generated from the sample are not detected. The principle of detecting the X-rays in WDX involves two other factors. Now, the X-rays which are generated, first they will fall on a crystal, or that is a diffractor. That is a crystal, which is mostly quartz-based crystal. And then after falling on the quartz-based crystal, they will diffract. They will diffract. X-ray will diffract. And now the diffracted or scattered beam, scattered X-rays will be detected by the detector. So now, in order to happen that your specimen and the crystal, which will diffract, and the detector, three has to be in the perimeter or periphery of the Roland circle. If you have studied the X-ray diffraction technique, then you will be able to know what is a Roland circle. So in the Roland circle, if the specimen and the crystal, which refract X-rays, and the detector, three placed in this um, Roland circle, then only the diffracted X-rays can be seen by the detector. So, here what we do, we filter the X-rays generated from the sample and selected X-rays which satisfy the Bragg's law. Selected X-rays which satisfy the Bragg's law are being detected by our detector in the WDS. So as we do not actually detect all the X-rays generated from the sample, rather selected X-rays which satisfy the Bragg's condition, certainly our peak width full width approximation will be narrower. So as only selected X-rays are detected, so the energy of the selected X-rays, the peak width of these selected X-rays will be much smaller, therefore giving us high resolution. However, the problem here is that the requirement of that specimen, crystal diffractor, and the detector has to be in the Roland circle to satisfy the Bragg's condition. There is a restriction that means of the size of the spectrometer has to be large. Size of the spectrometer has to be large, so that it would able to it would allow to alter the theta value, like in our Bragg's law theta value, while keeping both the crystals and the detector in the Roland circle. So first of all, size has to be much larger in case of WTX. Second point is that one crystal will not be enough. So in order to detect all the elements in the periodic table, 4 different crystals of different d spacing needed to be placed, needed to be there, so that we would be able to measure the X-ray energy of coming out of the atoms of all through the periodic table, lithium onwards. So the detection time or measurement time also now goes higher, because at a time, because all the crystals have a one particular d spacing, and therefore that would allow us to measure the X-rays in certain range. Therefore, another crystal will come with another d spacing, and that would allow in another range. So that we totally have to have 4 crystals to completely cover the X-ray energy to detect all the predictable element in the predictable. So analysis time is approximately 20 to 30 minutes in case of WDS, compared to 1 minute or less than 1 minute, 30 seconds in the energy dispersive X-ray analysis. So two disadvantages of WDS is that the size of the spectrometer has to be quite large, and the second is long analysis time, more than 20-30 minutes. So this restricts or this limits the utilization of WTS more widely as compared to the EDS, energy dispersive X-ray analysis. So this is another issue of the WDS. Okay. Another question was the bias voltage to the ET detector. Okay. So bias voltage to the ET detector. First of all, why we need to put the bias voltage to the ET detector? So ET detector or Everard-Thornley detector is a detector that detects our secondary electrons, or it can also detect the scattered electrons. So during initial years of the scanning electron microscopy, so Everard-Thornley detector was used to detect both secondary electrons and backscattered electrons. But nowadays, we have dedicated backscatter detector and we have dedicated secondary electron detector. So first of all, our secondary electron switches comes out of the sample, they have very low energy of less than 50 electron volts. So in order to collect as much of those secondary electrons generated from the sample, we need to apply a bias voltage. So if you remember, so we need to apply the bias, a positive bias in front of the detector so that it could collect more number of secondary electrons. So then not only just by collecting more number of secondary electrons will not be enough. So now they have to strike the scintillator with a high velocity. So when they do this with a high velocity, then they could generate more number of electron hole pairs, and that electron hole pairs will be utilized for the creation of the electron hole for generating the signal. Okay. In the meantime, there are few questions come. So let me discuss this. The lens used in SEM are made of which material, or please explain. First of all, remember that here the lenses are electromagnetic lens. Here the lenses used in the electron microscope are electromagnetic lens. There is no lens, physical lens, like that you see in our optical microscope. There is no physical lens. It is electromagnetic lens. You apply the current and generate a magnetic field, and with how much current you are applying and how much turn of those lines are there, that would those coils, magnetic coils are there. That would tell you what would be the strength of the lens. Particularly, if you check our lecture number 5. So there it is clearly discussed about how the magnetic lens are used. These are the magnetic lens. So electron beam actually pass through a orifice, and the orifice is surrounded by the electromagnetic lens. There is a iron cell, and there is a winding, and by applying the current and a number of turn would tells us how much strength of the lens, and with that we can control the focal length of the microscope. There was another question. Please explain the principle behind creation of image 2D, 3D in SEM, SIM, SPM. Okay, good. So this is a very good question. First of all three, SCM, SIM, and SPM gives us three-dimensional image. Three-dimensional image. It is not two-dimensional image. Three-dimensional image. What you take a simple camera and take a picture, you get three-dimensional image. That is what we get from our scanning electron microscope and scanning ion microscope and scanning probe microscope. 3D means, so you get X, Y, and in the Z. So up and down, like my hand is there. At the surface of my hand, I have my palm is not smooth. It is not flat. It is up and down. So some places I have more height, some places less height. So that is what I can get by this scanning electron microscope and scanning ion microscope. Moreover, on my palm there are rays. These rays can also be seen because the depth of those rays are different as compared to other places, creating three-dimensional image. Why it gives three-dimensional image by secondary the scanning electron microscope or helium ion microscope? Because the number of secondary electrons generated from different places, different height is different. If you look at the lecture number maybe 10 or 12, where I have written that the angle between the electron beam and sample versus electron yield, secondary electron yield. So as the angle between the sample striking, as the angle between the electron beam striking the sample surface is increases, then number of secondary electron generation become higher. So for example, you have a sphere. In the sphere, the side of the sphere have a larger angle of incident. So therefore, the size of this side of the spheres will be more brighter, giving us three-dimensional features. Or we have a mountains. So the slopes have a larger angle between the incident beam and the sample surface. And therefore, from those area, the yield of the secondary electron will be higher. Therefore, they will be more brighter. So this brighter and darker, brightness and darkness contrast, giving us three-dimensional image, both in scanning electron microscope and scanning ion microscope. But in case of scanning probe microscope, here, in case of scanning probe microscope, we have a physical probe that goes above the sample. It can be scanned with a constant height or constant current mode. And if I, let's say, if I scan the surface with a, let's say, constant current mode, in case of, let's say, scanning tunneling microscope, then I need to measure the constant current between the sample and tip. So in order to measure the constant current, if there is a upward, if there is a hill on the sample, my tip has to go up. My tip has to go up, because then only the distance between sample and tip will be same, and the same amount of the tunneling current will flow. So as tip goes up or tip goes down in a drop or in a pit, so therefore we will get a three-dimensional image in our we will get a three-dimensional image. There was a question whether metal coating applied to the biological sample if used in the helium ion microscope. You do not need metal coating in a helium ion microscope. That is what the advantage of helium ion microscope, that without a metal coating, we could able to get the measurements done and get good quality or clean image. So that is one of the advantages of the helium ion microscope. Because if you remember, if you remember correctly, I have told that means what is the what other things you can do to get the good image in a helium ion microscope without doing the without doing a metal coating. So that you can find in our lecture number lecture number 22 for imaging biological sample or other kind of insulating sample. In case of helium ion microscope, the beam current can be reduced to picoampere or femtoampere. It is because ion beam current produce much larger number of secondary electrons. Ion induced secondary electrons yield is much larger in case of helium microscope as compared to the scanning electron microscope. So that allows us, because the signal is more from helium ion microscope, we could use a smaller current, or beam size can be small, and we can use beam current can be small in case of helium ion microscope. When beam current is small, charging will be less. This is one of the way done by helium ion microscope. Another is that you use an electron flood gun that would neutralize the surface positive charge. So in that process, you can also get the good image without being charged using the helium ion microscope. So biological sample for another kind of sample can be studied by helium ion microscope without the metal coating, unlike in case of scanning electron microscope. As of now, we have very only a couple of helium ion microscope available in our country, and because of its relatively high cost. But in future, in next 10 to 20 years, the number of helium microscope utilization will increase as they become more promising in terms of several other features compared to the scanning electron microscope. But at the same time, the use of scanning electron microscope or field emission scanning electron microscope will not fade away for next 50 years certainly. Is there any more questions? I see there is no more questions. If there is no more question, we stop here. But certainly you can write email. We would be happy to answer your queries. And also we will have another live session. In that live session also, you can certainly ask me questions, even though from the initial lectures. So please feel free to write emails and or ask in the next live session.
Sir, wait for 30 seconds.
Oh, please explain what is the difference between FTA or SEM. Okay, let me explain. Fourier transfer infrared spectroscopy is used to measure or know the surface functional group of organic sample, particular organic sample. So that is a vibrational technique, that is also called vibrational spectroscopy, where infrared is passed through the sample, and then we study its absorbance or transmittance. At a particular infrared radiation energy, the particular functional group will make absorption, and that would lead to a transition of vibrational levels. If your sample has a dipole moment, then the vibration occurs, and you have a formula of that to actually know at what place the vibration will occur. So FTIR is completely a spectroscopic technique that is utilized to know the functional group of organic chemicals, such as, for example, if you have, let's say, water, or if you say carbon-carbon single bond, carbon-carbon double bond, carbon-hydrogen bond, or let's say ammonia group, primary amine, secondary amine, tertiary amine. You have acetic acid, you have alcohol, you have primary alcohols, secondary alcohols, you have ether, esters, all kind of chemicals, organic chemicals you can distinguish by FTIR. There is a completely different techniques for different purpose. On the other hand, scanning electron microscope is a microscopic techniques where you see the features to know its shape, size, morphology, etc. Any other question?
No, currently no questions.
Can we stop now then?
Yeah, you can.
Okay, thank you. Then should I just leave or what to do?
Just wait, sir. 30 seconds.